Anyone interested in displays or TV will be well aware that Samsung Display is developing a new display technology called QNED. The name of the technology, QNED, was first called by Samsung as a new technology, but LG recently released an LCD that uses mini LED as backlight under the identical name QNED. There is bound to be confusion. Perhaps it is problem caused by attaching several high-tech related words to give a fancy and advanced image to the general public, and it is true that they do not try to avoid confusion. QNED under development by Samsung is technology that consists of a number of very fine LEDs with a diameter of less than 1 micron and the lengths of about 5 microns. It is a technology that has a very strong potential to solve many existing problems of current display technology. If Samsung can realize the theoretically possible parts, perhaps Samsung's QNED is a huge technology that will dominate all display market. The question is it feasible? If the problem cannot be overcome, it will become an empty dream. Let's take a look at what problems they are facing now. Then we go on a tech trip. First, let's go over why driving each blue LED chips as a pixel is superior to conventional LCD or OLED once again, and proceed to the next step. Blue LED chips has high electrical efficiency over 80%. That is, when 100 electrons are injected into the chip, more than 80 blue photons are emitted. In the case of blue OLED, when 100 electrons are injected, about 10 blue photons are emitted. So the electrical efficiency itself is more than 8 times. It can be a quite big difference. If one uses quantum dot, blue photons can be converted to green or red with high efficiency depending on the type of QD. Also, the converted green or red wavelength is very narrow due to the characteristics of QD, so it has strength in color gamut. In addition, since LED is far more stable than any other light source on the planet, it is applied to the automobile headlights that requires very high brightness and durability. These excellent characteristics are being applied to the super large displays produced by Samsung and LG respectively, and they have secured visibility and stability in the outdoors as well as the flexibility to expand to the desired size. In this super large display that uses the blue LED chip, which is excellent in all performance as one sole pixel, there is no more rival and there will be no more in near future. However, the problem lies in the price of the chip as shown in the previous video. The number of chips required for 8K TV is about 100 million, and they need to be transplanted to the display panel by a method called pick and place. However, the price of the chip alone is over $40,000 based on current standard. 100 million chips are required for an 8K supersize over 100-inch, and the same number of chips for a 55-inch display. The price of $40,000 for a display over 100-inch can be justified, but it is bound to be a huge price for a small panel size. If the chip price is the same, of course, TVs with a size over 100-inch must be produced, because if the chip price alone for a 55-inch TV was $40,000, no one would buy it. If the chip size is reduced from 100 microns to 5 microns, 400 times more chips can be produced from one wafer, so the price of 100 million chips can be drastically reduced from $40,000 to $100. This will make it easier to solve the chip price problem. The chip to be applied to QNED is known as a rod shape rather than a conventional square shape, and is known to be about 1 micron in diameter. If successful, the chip price becomes almost negligible. Samsung's QNED has a strategy of forming one sub-pixel by applying 20 to 100 microchips made as above. The problem is that the pick-and-place process that transfers the existing 100 micron chips to the panel and attaches them to the correct position is no longer available because the chip is way too small. Numerous companies and research institutes around the world are developing the method, but no satisfactory method has been found yet. It is by no means easy to insert a chip of 5 microns or less into every 100. A new technology that tries to solve this in a new way is Samsung's QNED. A rod-shaped microchip with a diameter of less than 1 micron is used, and the self-assembly method is applied to insert the chip into the panel. Self-assembly technology is a method in which numerous chips sprayed by inkjet find their own place on the substrate. If we make a structure for the micro LED to sit on the board in advance and spray a large amount of LED with inkjet, the LED flows over the board and settles on the structure. The extra LEDs that are not seated in the structure can be recollected and reused. The patterned drawing on the screen shows a single micro LED chip that does not find its position inside the preformed structure. Numerous micro LED chips injected by inkjet cannot ignore the probability that they are positioned in this way inside the structure. In order to solve this problem, the patent also includes the contents of inducing the micro LED chip to take a seat by applying a voltage to the unstable micro LED chip. Tiny blue micro LEDs arranged in this way are grouped in dozens to form one sub-pixel, and each sub-pixel forms red-green quantum dots and red-green-blue color filters to produce RGB colors. This will form a sub-pixel. Even using the technology that leads to the alignment of these chips, it is impossible for all the chips that makes up 100 million sub-pixels to be in place. In the end, each sub-pixel is not equipped with a fixed number of micro LED chips, but sub-pixels with few chips are missing. It is impossible to plant extra LED chips again in a sub-pixel with a defect in the number, and Samsung QNED's approaches solve this by using driving method. After completing the panel, check how many chips are in each sub-pixel using electrical signals, find the correlation between the number and brightness, and then inject a current suitable for the desired brightness. This is an unprecedented method in existing display technology. The situation is different for each display panel, and the number of chips for each sub-pixel is different. It is expected that the success or failure of Samsung QNED will be determined by whether each pixel can be driven with the desired brightness. Besides this, another problem exists. When the chip size becomes smaller than 70 microns, the efficiency of the chip begins to decrease rapidly. If Samsung uses an ultra-small chip with a diameter of 1 micron or less for QNED, it is expected to show less than half of the efficiency of the existing blue LED chip. Of course, since the efficiency of the blue LED chip itself is already quite high, even if the efficiency is reduced to less than half, it will be still higher than that of OLED. In conclusion, it is a quite difficult display method. If successful, it can widen a huge gap with the latecomers and has the potential to neutralize the existing display method. However, it is likely that it will take a very long time to solve the above-mentioned problems and have the required degree of perfection for mass production. That's it for today. Goodbye.